Hi students, in this lecture I am going to discuss self-induction and mutual induction. Let us see. Let us now first focus mutual induction. Consider two conducting loops. Let us take both are facing each other. I am taking two conducting loops. So both are facing each other. Suppose this is coil 1 and this is loop 2. Okay, coil 1, coil. Assume that in coil 1 current is pass. Suppose the current is I, maybe clockwise or maybe anti-clockwise. We are knowing that a current carrying wire is producing magnetic field in the surrounding space. Now, this second loop is present in that magnetic field. Therefore, a magnetic flux is linked with this coil. And if we assume that this current is changing, when this current is changing, the magnetic flux linked with this second coil will change. And we have learned that whenever the magnetic flux linked with a coil changes, an EMF is induced in that loop, right? This is according to Faraday's. That means here current is flowing in coil 1, but EMF is induced now in second coil. So this is known as a mutual induction. Current is in coil 1, EMF is induced now in coil, and because of that EMF, current flows now in coil 2. And this is known as a mutual induction. Okay, and see carefully here. Flux in second coil, I am writing as phi suffix 2. Flux in second coil is proportional to current in first coil. Okay, or if I want to write here, means replace now this proportionality constant with equality. If you want to write here equal to, then we should write here one proportionality constant. That is now M, where M is known as coefficient of mutual induction. It is known as a coefficient of mutual induction. So flux linked with the second coil is equal to, this is a constant known as coefficient of mutual induction or simply mutual inductance, or it is simply mutual inductance. Mutual inductance. Okay, right. Now see from here, we can guess the units of coefficient of mutual induction. Flux is Weber and I is ampere. Therefore, units are Weber per amp, or we are taking it as a Henry, which is name of a scientist known as a Henry. Our notation is capital H, right? So here we are focusing that current flows in one coil, but flux is now changing in other coil. That means EMF is induced in other coil, and because of that current flows in the other coil. And this is what we call mutual induction, right? And if you want to calculate now that EMF induced, that is equal to, I'm writing suffix 2. This is the EMF induced in second coil, that is equal to minus d phi by dt, flux in second coil. And this is and this is equal to, in the place of 5 2, it is m into I. So minus m into di by dt. Okay. Rate of change of current in the first coil. Right. Let us now focus self-induction. See, coming to here, let us consider, so focusing now self-induction. Let us consider a solenoid. So taking a solenoid which is connected to a battery. Initially, switch was open, no current. And if you observe carefully, when switch is closed, then current starts increasing. It is not increasing suddenly. It is now starts increasing once switch is closed. And when current is changing, because of this current, flux linked with this solenoid also changes. And because of that change in the flux, an EMF is induced in the same coil. That's why this is known as a self-induction. See carefully, here current flowing in one coil, EMF induced in other coil. That is mutual induction. But coming to here, current is now changing in this coil. EMF is induced now in the same coil. That's why name is self-induction. Okay. And we are knowing that the direction of induced EMF, or you can say direction of induced current, it is in such a way that it opposes the cause of its production. Okay. So here we have to keep one important point in mind, that is, so here we have taken a solenoid where current changing because of that flux changing and because of that EMF is induced. And this property is known as inductance. I am writing here that property is known as inductance. Okay, right. Now see what we can do here. Coming to here, if you want to write equation like this, flux linked with that coil, that is proportional to current flowing in the same coil. Okay. Next, if you want to remove this proportionality here, write here proportionality constant into Y. So here flux and current both are in the same coil. That's what it is. This is known as coefficient of self-induction or simply self-inductance. It is just like coefficient of mutual induction. Okay. And units are same, Weber per ampere, or it is Henry. Okay. Right. And while solving problems, or before that, first focus here, EMF induced, that is equal to minus d phi by dt, which is equal to minus L into di by dt. Okay. That is EMF induced. Then see what we are doing here. Whenever an EMF is induced, we are replacing now inductor. That means a device which has the property what we call inductance, that is known as inductor. So inductor means it is having the property of inductance. That means because of change in flux and EMF is induced. Okay, it is known as inductor, and circuit symbol is like this. This is now symbol for inductor, which opposes change in current. Remember, it is not opposing flow of current, it is opposing change in current. If you remember resistor, Resistor is opposing flow of current. But coming to inductor, it opposes a change in current. That means if there is no change in current, this will be just like a conductor. It has no role. But if current changes, then an EMF is induced. So its role is now to oppose a change in current. If current is increasing, it tries to decrease it. If current is decreasing, it tries to increase it. So finally, what we are saying is it is opposing the change in current. Okay. For example, let us take current is increasing in an inductor. So circuit symbol is now like this. Let us assume current is increasing. Let us consider direction of current. It is towards right side. This is the current and this current is now increased. Now what happens is, since the current is increasing, an EMF is induced. And because of that EMF, a current flows. So here what we are doing is we are replacing the inductor now with an equivalent battery. See how to replace this? Since current increasing because of inductor, current must be opposite to this current direction. So I am replacing this with a battery and I am taking polarity. This is a positive and this is negative. So that because of this, current will be like this opposite. Because here current is increased. It tries to oppose the change. Since it is increasing, it tries to decrease it. That's why we are replacing this inductor with an equivalent battery like this. Okay. And for this battery, what is EMF? That is L into di by dt. And here I am not writing minus because that minus is for direction part. And here already we have taken the polarity. So now just focus what is modulus value. Okay. Now do one thing. Let us consider current is decreasing. Let us take current is now decrease. Then see how to take now an equivalent battery. Current flowing right side and this current is now decreasing. Then since current is decreasing, it tries to increase it. Okay. That means if you want to replace with a battery, it should be like this. Okay. And EMF is now L into, you should be very careful here. It's L into minus di by dt. See why I have taken here minus. Since the current is decreasing, di by dt itself is negative. Negative of negative positive. So this total value is now positive. So current decreasing, it tries to increase it. That means that battery has to send current in the same direction to support it. Okay. Like this, we can replace an inductor with an equivalent battery. Okay. Let us now focus problems. Let's see the first question. Calculate the self-inductance of a long solenoid having n number of turns per unit length. Question is given long solenoid. So for that we have to calculate now coefficient of self-induction. See how to calculate. So first focus now. Let us take this is now solenoid. Now in this current is flowing. Now see what I am writing here. So first we have to focus flux that is equal to L into Y. So first we have to focus what is the flux linked with this solenoid. After having the flux, divide that with current flowing in that. That gives coefficient of self-induction. Okay. So to calculate flux, phi equal to, you see, magnetic field inside a long solenoid. It is a mu naught Ni, right? This is a field into cross-section area of the solenoid. That is C. This is now flux linked with one coil, or you can say one turn. Now see number of turns. It is N into L. That means if you consider a length of the solenoid is now L. If you consider this length as L, then number of turns will be number of turns per unit length into L. Right? That is what I have taken. So mu naught Ni into A. This is a flux linked with one turn into number of turns. Right? Now this is equal to L into Y. So I gets cancelled from this. L equal to, see what we get. It is a mu naught N square A into L. A into L gives us volume of the solenoid. So from this what we can say is self-inductance is depending on the geometry of the given device, like what is the volume. And here in the volume of a solenoid, no material is present. It is air or vacuum. That's why it is a mu naught. If you are placing any substance inside in the volume of the solenoid, it becomes mu naught into mu r. There we have tried simply mu into n square into v, where mu equal to mu naught into mu r. So mu r is known as relative permeability, right? If you compare with the capacitor, there also we got capacitance depends on the geometry of the capacitor, like what is shape of the capacitor, size of the capacitor, separation between the plates, and what is a medium between the plates. So exactly same logic here also. It depends on geometry of the device. It depends on which medium is present in this volume. Okay. So like this, we can compare inductor and capacitor. And we can take one more comparison between these two. When it comes to capacitor, it stores electric potential energy in the electric field present between the plates. We are knowing that between the charged plates, in between these plates, electric field is present and electric potential energy is stored in this electric field. In the same way, coming to inductor, magnetic energy is stored in the volume of the inductor in the magnetic field. So here magnetic field is present. In that magnetic field, magnetic energy is stored. And here one more thing, if you remember while discussing capacitors, we have neglected the fringe effect. That means at the edges the field is not uniform. That is what we call fringe effect or edge effect. That we have neglected. In the same way, coming to long solenoid, we are saying that a field is uniform inside everywhere. Coming to at the edges, field is not uniform. So we are now neglecting that effect. So like this, we can compare an inductor with capacitor. Okay. So for a solenoid, what is coefficient of a self-induction? Mu naught n square v. Okay. Let us see next one. Let's see what is given. The length of a wire required to manufacture a solenoid of length L and a self-induction L is. Condition is cross-section area is neglected, right? Is asked now length of the wire required. Let us see. First of all, note down the given data. So we require, first of all, make diagram for solenoid. This is now solenoid. Let us consider now, it's already given that length is L. So this length is okay. And see which length we have to calculate. We have to calculate length of the wire. Okay. Let me take it as L naught, length of the wire. That is equal to number of turns into, for one turn, length equal to 2 pi r, right? If I am taking one coil, length equal to 2 pi r. Like this, if you have number of turns, n into L, this gives us number of turns into 2 pi r. That gives us length of the wire required to construct now this solenoid, right? Let us see how to make calculation. So we have learned, just now we have learned, coefficient of self-induction is equal to mu naught n square V, right? Now substitute values in this. Mu naught in the place of n. See what I can write. This is actually number of turns into 2 pi r, right? So I'm writing here n by n, okay? Whole square into V. This is now mu naught n square by L. See, in the place of volume, I can write A into L. This is L square. Okay. And here one L gets cancelled. Right. See, remaining what else left here? It is mu naught n square by L into A. Right. So, and what we have to calculate? L naught equal to n into 2 pi r. Okay. So, L naught equal to L naught is equal to n into 2 pi in the place of r. See what I can write? I can write here in the place of A. In the place of A, I can write pi r square. Right? I can write it is. I can write in the place of A pi r. So from this, I can get the value of r. Right? And substitute here the value of r from here under root of L, L, see carefully once, L, L, pi mu naught n square. Let me cross check once, L, L, mu naught n square pi, right? Now substitute that here, L, L, pi mu naught n square, right? Now see calculation carefully. N and n square gets cancelled, right? The remaining is now I'm taking 2 pi inside. It becomes a 4 pi square L, L, pi mu naught. Okay. Right. Now see what we get. 1 pi gets cancelled here. Remaining is now under root of 4 pi L self-inductance and L length of the solenoid upon mu naught. Means the result which we got in the previous question, that is mu naught n square V. Now we have taken that result to solve this problem. Okay. So here mainly confusion comes like what is this length and what is this length? This is length of a solenoid and this is length of the wire, which is 2 pi r into number of turns. Okay. And this is now coefficient of a self-induction or simply self-inductance. Right. So I hope you got the clarity. So coming to see which is the correct option, mu naught, or it is a 4 pi L by mu naught, right, under root. It is option A, right? That is the correct one.